Thank you. So let me continue the lecture of yesterday. So if I remember correctly, the number now should be 1.5. And well, we finished the lecture yesterday by an example of a Brahmanian abstraction for some norm varieties. And let me just give you a few more examples without proofs, where the Brahmanian abstractions are the only ones. So what is known? The Brahmanian abstraction to the Hasse principle and weak approximation are the only ones for the following examples. First case I want to mention, yeah, I didn't say it yesterday, but the Brahmanian abstraction was introduced by Manin himself in 1970. And in this paper, he essentially proved that the Hasse principle, the Brahmanian abstraction to the Hasse principle is satisfied for instance, principal homogeneous spaces of abelian varieties. And we will explain the words in a few minutes. But in a particular case, one gets the following result, that if you consider genus 1 curves, so smooth projective geometrically integral curves over a number field, assuming the finiteness, so assuming the finiteness of some Th average group of the Jacobian of this curve. So of course this is not known in general. So this is an elliptic curve, and if the Th average group is finite, then you get the Hasse principle and the Brahmanian abstraction. The defect of Hasse principle and weak approximation are explained by the Brahmanian abstraction. Yes, a slightly, well, a little variant of weak approximation is satisfied with Brahmanian abstraction. Another example, an easier example, well, no, not easier, but at least unconditional example, is a result by Kolliot-Hellen Sans-Suc and Swinart and Dyer. And it says that the result is true for so-called Chatelet surfaces, which are smooth projective models of the affine variety defined by the following equation. So you take an equation of this shape, so in 3 variables, where P is a polynomial of degree 3 or 4, and say a separable polynomial. So you can see it if you can fiber this variety of a P1 when you project to the variable x. So this is a conic bundle of a P1. And for these surfaces, the Brahman abstraction to the Hasse principle and to weak approximation is the only one. Another example I can mention. So of course the list won't be complete. Maybe one last example which we will explain in this lecture and maybe in the next one. So it's a result which is due to, well, many people in fact. Voskresensky, Sansuk, Bonvoy, and in fact many other people. I should put maybe Harder, Kneser, and so on, people working on semi-simple, simply connected algebraic groups. But the final result is in a paper by Borovoy. It said that this is true for homogeneous spaces of, say, connected linear algebraic groups with connected stabilizers. So varieties that are of a k-bar isomorphic to G mod H, where G is a connected linear algebraic group and H is a connected subgroup with connected stabilizer. So we'll come back to this result later on. So these are some examples. Much more examples are known. And yeah, maybe I can mention it now. And we'll come back to it in the last lecture. What is also known is that the Brahman obstruction is not the only obstruction in general. So, so this is rather a counterexample. And the first unconditional one was constructed by Alexei Skorobogatov. In 1999. And he constructed X. This is over Q, right, Alexei? Yes. A smooth projective surface, or so-called bi-elliptic. X, yes, for which you have adelic point orthogonal to the Bra group, but no rational points. So the failure of the Hasse principle is not explained by the Brahman obstruction. So there were conditional version of this example, which means that general conjectures, for instance, long conjectures, implies the existence of such counterexamples, but this one was the first unconditional counterexample. So, well, you can look at this paper and you have explicit equations for this example, but I won't explain it right now. Okay, so this was the first section about the generalities about the Brahman obstruction. Now, I want to focus on the third example here, and to make the connection between this result by Borovoy and the the lectures by David Harari and the arithmetic duality theorems. This will be the content of the second section. So let's say Brahman in abstractions. For homogeneous spaces of algebraic groups. And just to explain the words in the statements, I need first to explain, so this is 2.1, the notion of, well, homogeneous spaces, and more precisely, we will start with principal homogeneous spaces, also known as torsors. So, torsors over a field, and a connection between torsors and Galois cohomology. And so to consider to prove the result above, we will first consider the case of commutative algebraic groups. So essentially it's the case of tori and of abelian varieties. And but in the final result, we do not assume that the group is commutative, right? It could be GLN, or you prefer an orthogonal group, or any kind of algebraic group. So I have to make general definitions of torsors and Galois cohomology in a non-abelian setting. Okay. So definition. For simplicity, we will fix a field of characteristic 0. Or in the end, we will apply this to number fields, so it's fine. For people who want to make a more general version of the statements that will follow, you can adapt it to an arbitrary field, but you have to be a little careful about what you call an algebraic group. You have to put some smoothness assumptions, and you have to replace the algebraic closure by the separable closure. And essentially, it works the same. But for safety, we will keep this assumption in mind. And for people interested in more general setting, in the last lecture, we will consider torsors of an arbitrary base. So we will generalize this later on. So the definition of a torsor is the following. So yeah, everybody knows what an algebraic group is, right? You in the lecture.
I assume that.
Yeah. Okay. So I assume it too. Well, in particular, in this setting, an algebraic group is always smooth, so you don't have to worry about non-smoothness. So definition. So let G be an algebraic group. Of K. A K-torsor under G, which is sometimes called also a G-torsor over K. Okay. Is a non-empty K variety together with an action, say an algebraic action of J, G, which means a morphism of algebraic varieties over K. satisfying all the natural axioms that you would ask for this to be a group action, right? With an algebraic action of G. So this is just for the while. This is a definition of a variety with an action of an algebraic group, and you ask. So we can phrase it in various ways. For instance, fix an algebraic closure k bar over k. And you want that this action, we want this action to be simply transitive, free and transitive over k bar points. The action of gk bar and xk bar is free and transitive, which means for any 2 points in xk bar, you can find a unique g in gk bar such that y is, oh yeah, I have to choose between left and right. Sorry. So I will consider right actions. So this is the definition of a right torsor. Okay? Of course, you can define everything on the left. So here I will write it like this. Okay? So I hope I will be coherent in the whole lectures, that all my action will be on the right. Of course, everything is the same on the left, but the formulas can be a little different. In a more geometric way to phrase the last condition here is to say that the natural map so you have a map from x times g to x times x, given by, so I write it here, x, g maps to x times g. This map is an isomorphism of k varieties. Okay, this is equivalent to saying this. Okay, so this is a definition of a k-torsor. Maybe I will give a few examples. So the first example is the case when x equals g, equipped with the action of g on itself by right translation, with action by right translation on the right. It clearly satisfies the definition, and this is called the trivial torsor. Second example, for instance, you can consider x to be yeah, I am characteristic 0, so no. Consider this variety. So the square roots of -1 in k. This is a natural k-torsor under mu2. Well, you can think of mu2 as z mod 2. Okay, this is the same because we are not in characteristic 2. of course, you know that, well, there is no preferred, you cannot choose a canonical square root of -1, but once you have one, you get the other one by changing the sign, okay? The example here, a genus 1 curve is a torsor under its Jacobian variety, which is an elliptic curve. Yeah, and to come back to yesterday example, we considered varieties defined by affine variety defined by norm equations. So such a variety here is a torsor, a K-torsor. Let's try to keep the notations coherent. Is a K-torsor under the torus say of equation, the K-torus of equation norm equals 1. C is non-zero here in capital K, and as you can see, once you have a solution, well, this group acts on this one, and in a simply transitive way. Okay, so here is a list of examples of torsors. So,
I'm sorry.
Yeah.
Is this third example not true for higher genus curves?
No, because if the genus is higher, this, if the genus is G, this will have a dimension, this will be an abelian variety of dimension G, so you have a problem of dimension. So a torsor has the same dimension as the group that acts on it, because it is, at least over K bar, they are isomorphic, so this is specific to genus 1. Yeah, so an important and easy result for torsors is the following one. So if X is a K-torsor under G, for any field L containing K, and for any point in XL, the morphism, so you can map, you can extend G to an L group. You can map it to X, extend it to L with the obvious map, the action on the given X. And this is an isomorphism. So an isomorphism of L torsors. Okay, I didn't mention it, but yeah, I should mention it maybe now. Sorry. So if you pull back a torsor, you get a torsor under the pullback of the group. So it's an isomorphism of L torsors under GL. And I didn't define what a morphism of torsors is, so I should do it now. So remark, a morphism of K torsors under G is a G equivariant morphism Okay, this is just a morphism of algebraic varieties, but which is G equivariant for the actions on X and Y. Okay, so this is what I mean by this, this sentence here. So why is it, well, this is essentially obvious to prove this proposition, and essentially this is a consequence of this condition of, well, here. And what you get from this proposition is that you get an alternative definition of a torsor. We could have defined torsors as K forms of the trivial torsor. Okay? A torsor is just something defined over K with an action of G, which becomes isomorphic to the trivial torsor with a natural action over K bar. So this would be an alternative definition of a torsor. Okay? A second proposition, which is an easy consequence, for instance, of the previous one, is that a morphism of torsor is necessarily an isomorphism. A morphism of K torsors under the same group G is an isomorphism. Because essentially, if you've got X and Y, both become isomorphic to GL over some finite extension. And then so the obvious diagram is commutative. And this forces this one to be an isomorphism. Okay? So you can rephrase it by saying that the category of torsors under G is a groupoid. Okay? Right. An important result. Oh, yeah. For the to use descent, Galois descent in the following is the theorem that I won't prove, but we will use it at several parts. So a theorem, oh yeah, theorem. So first, algebraic K groups. Well, yeah, algebraic K groups and their K torsors are quasi-projective varieties. And we call that quasi-projective means they're isomorphic to an open subset of projective space. Quasi-projective. Sorry? Yeah, of a projective variety, sorry. So for instance, they could be affine, they could be projective, and there could be some kind of mix of those two parts. Okay, so for the case of groups, this is a consequence of a theorem by Chevalet that says that a connected algebraic group is always an extension of an abelian variety by a linear, which means affine algebraic group. Okay, so maybe I will state the theorem later on. This will be interesting because we will be able to apply Galois descent to this kind of varieties. And as mentioned in the title, I want to relate the notion of torsors with the notion of Galois cohomology. So let's define Galois cohomology in this non-abelian setting. So G is a K algebraic group, or an algebraic K group. So define H1 So I will define two objects. So first, say something that we can call H1 tor kg, which will just be the isomorphism classes of K torsors on the G up to isomorphism. Okay, and the second H1, which will be a cocycle H1, which will be the set of equivalence classes of cocycles, say C from, but this denotes the absolute Galois group of K with respect to the fixed algebraic closure here. So you consider cocycles, which are maps from gamma K to the K bar points of G, satisfying the cocycle condition, which is something like C of sigma tau is C of sigma, sigma C of tau. So this is the natural Galois action on GK bar that I denote like this. Okay. The set of equivalence classes of cocycles for the relation, for the equivalence relation. So what do I mean by that two cocycles are equivalent? Just so the equivalence relation, we say that two cocycles C and C prime are equivalent if and only if one can find, let me write it in the correct direction. So K bar point in G, so that for all, say gamma, C prime of gamma is G minus 1, C of gamma, gamma G. Okay? So in particular, cocycles of the shape G minus 1 times gamma G are trivial cocycles. Well, this definition is this cocycle definition is quite natural if you think of the cocycle description of the Galois cohomology, of the Galois H1 in the abelian setting that you define in the lecture by David Harari. Yes?
I think you want your cocycles to be continuous.
Yes. Yes.
Locally constant.
Yes, yes.
Because here you take the whole Galois group.
Yeah. Of continuous. Thank you. Well, here you put the profinite topology, and here's the discrete one. Well, as in the. Did you mention the? Yes. Okay. Perfect. And the key point is the proposition that says that both H1s are the same. Okay. So this is the connection between torsors and Galois cohomology.
Even without not the zero characteristic assumption.
Yeah, you can, yeah. So if you take the correct definition, well, probably the definition here as, the first version here, if you put K bar, if you replace K bar by the separable closure, is not enough to have the correct notion of torsor. You should choose this version. But otherwise, everything works the same if you put the separable closure And if you assume that G is smooth.
Yeah.
Okay.
It doesn't have to be replaced by SPPF.
Yeah.
I see.
Yeah. Everything is étal here, or Galois. Okay, so the proposition is just that, yes? This one, up. Not this one, but this one. Is it okay? Oh, yes, because of the, sure. There is a natural bijection. Yeah, so as you can see, I just wrote set here, not group. So this is not a group, but this is a pointed set because you can consider the constant cocycle equal to 1. And similarly here, this is a pointed set because you have the trivial torsor, which can be seen as a trivial point here. So there is a natural bijection of pointed set. Between H1 tor K G and H1 cocycles K G. And if G is commutative, both are isomorphic to the classical H1. So in particular, you get that you have in the abelian case, you have a group structure on the set of torsors, which we will explain later on, a geometric way of describing this structure. Yes?
Yeah, I was just going to ask the following naive question. If you take the group structure that you find in the commutative case and you try to mimic it and produce some sort of, not necessarily group structure, but map, what fails?
I'm not sure to understand.
So what
Is there any more structure than just a set? Like, do you get anything with a set? This definition?
I mean, if you assume that G is commutative? No, G is arbitrary. I think you cannot. So in general, you have no more structure than a.
There is no functorial group structure.
Yeah, you cannot do something reasonable in a very general setting. We will see that in some particular cases you can do something if you replace G by something that is not an abelian, well, which is a cross module, for instance. So there is a notion of cross module, which is something in between an abelian group and a general algebraic group. Then you can put more structure on this set. But in general, there is no way. Well, we'll see something that is kind of a group structure, a product of torsors, but you have to change the group. There is a twist involved. So the set is not stable, so unfortunately. Okay. Well, if you consider bitorsors under G, then you have some group structure. But I don't want to mention bitorsors right now. Okay. Oh yes, or maybe I will just explain the proof. Well, give the maps. So I have to define a map in both directions. So given if P is a torsor, a K torsor under G, choose a point, say a k-bar point. Of course, you can do everything at a finite extension level. But choose a k-bar point. It exists because, and this is important, because I put non-empty here. If you remove non-empty, you get a notion called pseudo-torsor, and you really want to have points to get a cocycle, okay? So you choose a point, and you look at how the Galois group acts on this point, okay? So for any element in the Galois group, you have you have x and gamma x, which are 2 points of the same, of xk bar. So they are not equal, but the difference is, so I use this axiom here. The difference is an element in G. So gamma x is of this shape for unique G gamma. I mean, G gamma will be the cocycle we are looking for. Then is a cocycle. Well, you have to check it, but this is because of uniqueness. You have a relation between G gamma gamma prime and G gamma times gamma G gamma prime. So this is a cocycle, and you have to check that if you choose a different point, you get an equivalent cocycle, and if you choose a torsor that is isomorphic to P, you get an equivalent cocycle. Okay, so choosing another point in xk bar, or in is it x or p? P. In pk bar, or another, or a torsor q isomorphic to p. These two changes lead to an equivalent cocycle, to equivalent cocycles. So the map from the left to the right is well defined. Okay. So let's now go to in the other direction. No, not this one. No. Yeah, this. Okay. So in the other direction, we will use Galois descent. And this is the place where we will use the fact that the torsors are quasi-projective. And this difficulty here, the fact that we need this assumption, is because I gave a definition of torsor, which I asked the torsor to be varieties, to be representable by a variety or by a scheme. If I just ask the torsor to be a sheaf, then I don't have to care about descent. So this geometric property here is necessary just because I put some representability condition on the torsors. So in the other direction, so given a cocycle, so say C gamma, define a twisted Galois action of the Galois group on the set, say GK bar, by so you want. So this is okay. This is so for all x in GK bar, you define a new Galois action by, of course, using the given Galois action. So this is the given Galois action. This is the new one I'm defining. And you twist it by the cocycle C gamma. Well, G gamma maybe is better here. You twist it by G gamma on the right. Maybe I should put some minus one. Oh, no, it's on the left. Yes, you consider this. Okay, this lives in the group. So in the group, I can multiply on the left or on the right. So I multiply on the left, so that now I will have an action on the right. And so this is check, this is a group action because G gamma is a cocycle. Okay, this is a group action. And G bar is quasi-projective. The quasi-projective variety of a K bar. So if you have a quasi-projective variety together with a descent data, which is exactly an action of the Galois group on the K bar points. Galois descent. So this is Galois descent. Tells you that this variety together with this Galois action comes from a K variety. So this data defines it defines a K variety, say P, so that when you pull back to K bar, you get GK bar with this Galois action, okay? Such that PK bar is isomorphic over K bar to GK bar with the twisted. So this is Galois equivariant if you put here the twisted Galois action, twisted action. Okay, so this is Galois descent. And so the variety descends to K, and also the action. So you have a natural action of GK bar on the right here, just by multiplication on the right, right? G act on itself both on the left and on the right. So you act on the right, and this action also descends. And the action, the right action, of GK bar on itself also descend. So in some sense you use the descent for varieties and also for morphisms. Also descends to an action over K. Okay? And then you only have to check that this is a torsor. But to check this is a torsor, you can go up to K bar, or you just get PK bar is GK bar with the translated action. P is a torsor. Okay, since essentially PK bar is GK bar via this isomorphism here. Okay. Okay, so it proves it contracts the map from cocycles to torsor, so from the right to the left. You have to check that this is well defined. So if you take equivalent cocycles, you get isomorphic torsors. This is easy. And this is done. It's easy to check that this map is a converse map to the first one. Okay. So it proved the proposition that relates Galois cohomology to torsors. So from now on, all these sets, so all the H1 will be denoted by just H1, and I will talk about torsor or cocycles, or okay, will be denoted by H1 K G. Okay. And if I need it, I will put some étal if I have some other cohomology later on. Okay. Okay, so H1 classifies either cocycles or torsors. So of course you can also define H0. H0 of a non-commutative group is just the set of rational points of the group. Unfortunately, it's much more difficult to define H2 of a non-abelian group. So it's possible, but it's more technical. So I think I won't speak about it in these lectures, but there is a definition, and for higher cohomology, it's really complicated. Okay, so this is the definition of torsors. Now you know everything about torsors. So now we can move to the Brahman abstraction for commutative algebraic groups first. So this is 2.2, I think. Brahman abstraction for tori and abelian varieties. So we want to prove that given a tori, or an abelian variety, and given a torsor under this torus or this abelian variety, is the Brahman abstraction to the Hasse principle and to weak approximation the only one for such a torsor. And so the setting is so now K is a number field. OK is a ring of integers, and U is a non-empty open subset of OK. And as David already explained in the, recall in this last lecture, we have the Hartin-Verdier duality. So if F over U is a group scheme say, what assumption do I need here? Say a finite étale group scheme. And n is an integer invertible on U, such that F has n torsion. So in this setting, David explains that we had the Hartin-Verdier duality theorem. So Hartin-Verdier so there is a natural exact pairing of finite group given by cup product. HR, say HI, U, F. So maybe just put H3 minus I times HI with compact support of the dual. What was your notation for the dual?
F prime.
F prime? Okay. So I will try to keep this notation. With value in H3 with compact support of GM, which was canonically identified with Q mod Z. So you have a duality like this, where F prime was the Cartier dual, which means the home sheaf between F and GM, which in this case is representable by an étale group scheme. So this was a Cartier dual. Okay? So we had this duality in étale cohomology, and now we are interested not only at finite group schemes, but at tori and abelian varieties. So now let T and say curly A be a U torus, respectively an abelian scheme over U. So the definition of a torus over U is the same as a torus over a field, essentially. Locally, for the étale topology, it becomes isomorphic. This is a group scheme that locally, for the étale topology, it becomes isomorphic to some power of GM, okay? And an abelian scheme is essentially the same definition as an abelian variety, but over an arbitrary base. And we will apply this just to well, in the end, we will have a torus on an abelian variety over K. We will extend it to a small neighborhood, to a small open subset of respect of integers, to a torus or an abelian scheme. So this will be the setting in the end. So given such a torus and such an abelian scheme, well, you can construct, well, first you have some dual objects. So here you see you have F and this dual. So we have to consider the dual of T and the dual of A. So dual object. So the dual of T, I will denote it by T hat. It won't be a torus here. It will be the same definition as here. So this is the Ohm sheaf between T and GM. And if you think of the case of a field, if you put GM here, you get, if T equals GM, you get Z. Okay, morphism to GM, from GM to GM. So here you got something that is an étale sheaf, or a sheaf for the étale topology that is locally isomorphic to Z to the R. Commutative group sheaf, étale locally isomorphic to some Z to the R. R is the rank of the torus. Okay. So this will be the dual of the torus. And what will be the dual of the abelian scheme? Well, I will put A star here, or A star. And unfortunately, or fortunately, I don't know, the morphism from A to GM, all such morphisms are trivial. So we have to consider something different. Well, and if morphisms are trivial, we can look at X1. You can define an X1 sheaf from A to GM. So extensions of A on the right by GM on the left. And you can prove that this is represented by an abelian scheme. So this is an abelian scheme over U. You can identify it with the Picard, if you know it, the Picard scheme, pic 0 of the scheme A over U. So you get two descriptions of the, yes?
Is the hat always representable?
Or? This one? Yes, it's representable by a, say, group scheme, but it will be a...
It's a group scheme, but not of finite type.
Yeah.
So it is not an algebraic group.
Yeah. I could put, I can put scheme here. Okay. Well, yeah, well. Well, instead of étale sheaf, I could put scheme. Okay.
So maybe we should say that this X is taken in the category of
yeah,
it's a bit subtle because
yeah.
Like either FPPF or category of commutative.
Yeah. Well, yeah. Maybe the more natural is to take. Well, you don't have to. If you don't want to ask questions about representability, you just consider the FPPF X1 between those two in the category of FPPF commutative group sheaves. You have this X1, and I think it is automatically this is the same as the X1 in the category of commutative group schemes.
yeah. This category is a bit subtle because there are no injective objects.
Yeah. That's why I prefer thinking about.
Take your data.
Yeah. So it's a bit subtle too. Yeah, there's subtlety about this definition here. Well, in the end, what we will do, we will define A and A star over K, and we will extend them to some finite, to some little open subset. So all you have to care about is the definition of the dual abelian variety over K. Yeah. Okay, so you have dual objects, and what is nice is that you can, but of course, well, both the objects and the duals are not finite in some sense, so we cannot apply this duality theorem. But for any n, say invertible on U, you can consider the n torsion of the torus T. Okay? So this is just the kernel of the multiplication by n on T. And you can consider the co-kernel of the multiplication by n on T hat. So it's something that is locally of the shape z to the r mod n. So both are finite étale group schemes. So this is something that looks like mu n, and this is something that looks like z mod n. Okay? So these are dual finite étale group schemes. And similarly, you can do the same with a curly A. You can consider an and a star n. Both are finite. Well, if G is a dimension, this is locally something of the shape z mod n to the 2G. They are also finite étale group schemes. So you can apply this theorem to these torsion, the torsion part of the object we defined, and you get, so you replace f by this object, so you get duality results, and then you pass to the limit. You make n vary, and you pass to the limit, so you get a duality for essentially for T on A. T on A. So of course you have to take, if you fix U, you have to take only n invertible on U. So how do you pass to the limit in such a setting? Well, you take n to be the power of some invertible prime number, and you take higher and higher powers, okay? So you get, so after some work, you have to check that when you pass to the limit, well, you have to check about the exactness of the limit and so on. Yeah, I didn't mention it, but of course there is, these are, I did not explain in what sense they are dual. So you have, well, you can see it here, but you have a pairing from T cross T hat to GM, which is obvious. And also you have a pairing from A times A star, not exactly to GM, but to GM translated by 1 or minus 1 because of this 1 here. Okay? So you can see it in some sense as morphism from A to GM shifted by 1. So you get a pairing from A times A star to GM shifted by 1. So if you put all of this together, you get natural pairings from H 3 minus I U T. So L is prime invertible on U. And this is the L primary torsion. Okay? So this is the limit of all L to the n torsion when n goes to the infinity. H I C U T hat L torsion with value in Q mod Z. This is just obtained as a limit of this result applied to these schemes. So you get something like this. And since it is perfect at a finite level, you will get this is essentially perfect at the limit, but you have to be a little careful. So you got the same thing for, except that you have hi c u a hat l q mod z. Okay, here I put 2, here I put 3 because of this shift I mentioned before. Okay, so you get natural pairings like this, and the fact that these pairings are exact for the n torsion gives you information about the exactness of this pairing for the whole T and the whole of A. They are not exactly exact, but they are exact up to the divisible elements. So if I put some bar everywhere, so L is a prime, and if you take a group, say, for an abelian group A, B, so B bar is just B quotiented by the subgroup generated by there. Thank you. The maximal divisible subgroup of B, which is in general not the same as a subgroup of divisible elements. Okay, so if you mod out by divisible, essentially if you mod out by divisible elements, these pairings become exact because it was exact for F equals n torsion of A and n torsion of T. Okay, so this is very fast. The real proof is more technical, of course. You have to check everything and pass to the limit and so on, but oh, this one, this is really the L primary torsion, yes. Yes, I have to write it, thank you. And BL is just the union of L to the n torsion. And BL. Okay. So now we have Artin-Verdier duality for tori and abelian varieties, abelian schemes. So we can prove we can deduce, now pass to the limit on U. So taking the limit on U, so you get U smaller and smaller, you will get information about what happens over K. And you will get the following theorem, which is you have a Poitou-Tate exact sequence for T and A. So K is a number field, so T over K is a torus, A over K is an abelian variety. Then, so this is due to say Milne, Harari, and Samueli. So there is a Poitou-Tate exact sequence of the following shape. So it's good to have a big blackboard to write these sequences. So for the torus, you get something like H0, K, T. Well, this is profinite completion, okay? The restricted product of H0, KV, T, profinite completion, H2. So you have to compare this Poitou-Tate exact sequence with the one for finite Galois modules, and this is very similar. So this is a dual here. Was it the notation you used for?
Yes.
Yes, thank you. Here you get the direct sum of H1 KV T. So here you get H1 K T hat dual. Then you got H2 K T direct sum of. So this exact sequence here is a generalization of Brouwer-Hasse-Noether theorem when T equals GM. And here you get H0 of K T hat dual, and this last map is surjective. So I have a 9-term exact sequence relating global information on T and local information on T, okay? And a similar one for A. So I won't have time to write it for A, but it's, here you have 9 terms. I think for A you have 10 terms. It's slightly different, but it looks formally essentially the same, and a similar one for A.
What is this notation? Is this a product?
So this is a restricted product. Oh yeah, maybe like this? Yeah. Okay, sorry.
The check is dual with respect to the others.
So this, so which one? So, oh yeah.
The check.
This one?
No, the other one.
This one? Yeah, yeah. This one is profinite completion.
Oh.
Yeah, yeah. I'm sorry about the notations.
You have parts up and wait. Not just
Yeah. So B hat like this for an abelian group is just the profinite completion. So the inverse limit of all the finite quotient of B. Yeah. If you do not put the profinite completion, this is not exact. So you really need this one. And well, there is a subtlety here. You have, of course, you have to put for the infinite places, you have to put the modified H0. So you have to mod out by well, the usual modified H0 for infinite places. And I think, yeah, I think I will stop here because we will explain this afternoon how to deduce from this duality result the result we want about Brahman obstruction for torsors under a torus or an abelian variety. Okay, I stop here.